Hi folks, today I want to talk about combining ideas of energy with work. And in particular, I want to talk about what modifications we can make, or what modification really we can make to E initial equals E final if we have work being done that changes these two things. So I want to deal with situations where this equal sign isn't valid, and we have more initial energy than final, or more final than initial. So that's where we're heading. So I would say our topic is combining conservation of energy with work. So that's what we're going to do right now. So question one is, I want us to think about, I want us to split work into two different types of work. So I'm going to think about work in general, and I'm going to split the work into two sort of subtypes. This is just conceptually organizing our thinking. Sometimes there's work that's done by conservative forces, or work due to conservative forces. And I'll tell you what I mean by that in a minute. Actually, I think I'll tell you what I mean by that right now. So work due to conservative forces means that the conservative forces have an associated type of potential energy. Right now, depending on when you're watching this, you may only know one conservative force, one force that has an associated type of potential energy. So we may just have gravitational potential energy, but there are quite a few types, actually, of potential energy. So if you take a spring and stretch it out, you can associate a potential energy with the stretch in the spring. And so there would be an associated force with that called the spring force. Magnets, charges, and other things as well have associated types of potential energy. And this is a very general discussion right now, so I want to kind of give you the big picture. The big picture is work due to conservative forces is kind of one type of work. Work due to non-conservative forces is also, like, these are two basically helpful categories. Work due to non-conservative forces. Changes something. Now I want you to take a minute and think about work due to non-conservative forces changes something about a system. So I have a system, I don't know, it's this eraser. I'm going to exert a non-conservative force on it. I'll give you examples of those in a minute, but let's just think about the language of this. If I exert a non-conservative force on a system, what do I expect to be changed by that force? Pause the video for a minute and see if you can come up with a guess for what I'm going to fill in the blank here. All right, hopefully you pause the video. It changes the total energy of the system. Okay. Because it's non-conservative, right? Conservation means energy initial equals energy final. So non-conservative means that type of work is going to change the total energy. It's not going to be E initial equals E final anymore. Changes the total energy of the system. Okay. Let's get a little bit more concrete, because this sort of feels like just terminology here. So let's talk about some examples. Okay, so examples of conservative forces, or let's do non-conservative. Examples of non-conservative forces. You should actually be able to rattle off a list of at least a couple of forces that are non-conservative, really without me adding any more info. I'm just going to remind you, non-conservative means that this is a force that can change the energy of a system. So here's my system, just an eraser. I want to change its energy. What kind of force should I exert on it, or what kind of force could be exerted on it to change its energy? Well, a push, right? Push or pull, right? Just a person or some other kind of agent coming in and pushing that system from the outside, that is an example of a non-conservative force, as long as there's a displacement in the same direction as that force. So that's one example. What else could change the energy of this block? Well, if the block's sliding along and it's sliding to rest, it's losing kinetic energy. That kinetic energy is not getting stored as anything else. It's turning into thermal energy, which we don't normally keep track of in our E initial or our E final. So friction is another example of what is often a non-conservative force, kinetic friction in particular. Could be something like tension from a rope, potentially. If you're using a rope to pull something, then it's kind of another example of F pull. But these are examples of forces that can be non-conservative, and often are. The question of whether a force is non-conservative is it changing the energy of the system? And so when we want to talk about the work due to non-conservative forces, the work due to non-conservative forces, that's the symbol we're going to use for the work due to non-conservative forces. Okay, so let's do a really simple example and make it a little more concrete. So let's say we have a frictionless surface here, and that's supposed to be horizontal. Again, we'll make it a little more horizontal. And I have a box on that frictionless surface. Let's say it starts out at rest, and let's say I give it a push, right? And so later on this frictionless surface, it has some velocity that's bigger than 0. I don't know, I'll give it a number, say 10 meters per second. Okay, so my push is a non-conservative force because E initial here is 0. There's no kinetic energy, it's on the ground, there's no gravitational, there's nothing else going on. So initial energy is 0. The final energy, this is moving, so it has some kinetic energy. So I have E initial, and it doesn't equal E final. So I'm going to write down an equals with like a question mark, because it's not an equals. And I'm going to write down E final. Okay. Now in this example, which one of these is bigger? Well, just hearing me talk through it and say this one's 0 would lead you to believe that this one is bigger, and that's correct. So I'm just going to write big down here, just to remind ourselves that that's big. This is small. It actually happens to be 0. So in this case, these are not equal. The work due to this non-conservative force is either positive or negative. And I want you to pause the video and think for a second. Is the work due to this push positive work or negative work? Okay, hopefully you thought about that and came up with an answer. The work due to the push is positive because the force points in that direction, the displacement points in the same direction, delta x. So when the force and the displacement are aligned, the work is positive. So this is an energy change, right? This work due to the push is a change in energy. It's a change in energy that accounts for the difference between the small and the big energy. So what I want to do is I want to add this number, this work push, I want to add it to one side of the equation or the other to balance out this equation. So where does it go? Well, it goes on this, it's a number greater than 0, so it's going to need to go on the small side, like that. And now we are going to be able to write that E initial plus the work due to our non-conservative force equals E final. And now we have modified the conservation of energy formula correctly so that even when we have non-conservative forces, we can still use this. It's no longer conservation in the narrow sense of initial equals final, because we have this other term, but essentially we have initial plus this transfer of energy. In this case, a transfer of energy into the system gives you a final energy. So let's take a look at another example and see what happens when we have sort of something slightly different going on. Okay, so let's have a system with friction. So there is friction on this surface. We'll have another box, and we'll have this box initially going 10 meters per second. And then at the final, we'll say that it's going 5 meters per second. And I'm also going to say that, I'm also going to say that you're pushing it. So there's an applied force, a push, F push. But whatever you're pushing, you're obviously not pushing hard enough to make this box speed up. So you're pushing along in this box. It was already going 10 meters per second to the right. You're pushing along, trying to make it keep going, but you're not really succeeding. So this push is actually, I guess maybe we'll draw it small just to make it visually clear. You're kind of just half-heartedly pushing this box along. So let's write down conservation of energy with our new modified version, and figure out how we would represent this. So let's do our energy bar chart. So for starters, so this is initial. For starters, we have some kinetic energy. And then finally, we have some kinetic energy, but it's less. And that's it. We don't have any other types of potential, right? Friction has definitely created some E-thermal. And but for when we're using the work due to non-conservative forces, we are not going to represent E-thermal on our final. I'll clarify that in a little bit, but I'm going to leave E-thermal off. So we have kinetic energy initial, we have kinetic energy final. Clearly these don't balance, but I want them to balance. I want to use my energy bar chart idea, and I'm looking at this formula down here, and I want to know how I can modify this so that this, the sort of total bar here, the bars adding up here, will add up to that. So, and I changed my mind. I'm actually not going to do a push for this first example. We'll come back to that one. Okay, so my apologies to those of you taking notes in pen, but too bad. All right, so this is just friction. It's just sliding along like this. We've just got friction. So what direction is the force of friction? Well, it's sliding this way to the right. So friction points to the left, okay. But delta x points to the right. So is the work due to friction positive or negative? So the work due to friction is negative because the force points against the displacement. And so the work due to this non-conservative force is going to be a negative work. And so just like we put it on this equation, we also put it as a negative value here. And we call that the work due to non-conservative forces. In this case, you could also just as easily call it the work due to friction, because that is the non-conservative force. And now you can see that these bars, at least plausibly, could add up to that bar. And so you have this formula represented as an energy bar chart here. And it's the same formula. You don't need to change a minus sign here. This is always a plus. But then the work due to non-conservative forces itself, this value here, sometimes it'll be positive if the force aligns with the displacement, and sometimes it'll be negative if the force goes in the opposite direction of the displacement. So the tip here is to leave E-thermal off of energy bar charts if using the work due to non-conservative forces. Essentially, you can think about it, this is just optional. So if you're just sort of like barely holding on and this just makes sense, but you don't want to like stretch too far right now, because like you just want to consolidate what you have, you can ignore what I'm about to say, just for like the next 30 seconds. So you could track this as the work due to non-conservative forces, which is the method we're doing, or you could track this over here and call it E thermal, because it turns out that E thermal is created by the work due to non-conservative forces in this case when it's friction. So when it's friction, it can either show up here as a negative value or it could show up here as a positive value. But actually, just don't do that. Don't do it over here. Leave it down here, and we'll call this the work, again, due to non-conservative forces. Okay, so I want to show one more example. An example where, going back to that example, I want to put the push in and show how you can do your energy bar charts. So let's start from scratch. Here, again, we're still using this. This is sort of our master core formula here. And I have, again, a situation with friction. Okay, and again, I'll have my box slowing down. I'm not really using numbers, so it doesn't really matter. But I'll make it a different value just for variety's sake. And so friction, so the velocity is going that way, the friction is going to be going this way, Fk. And let's say that you're trying to push this thing, right? But you're not doing a very good job, and so it's still slowing down. You're half-heartedly pushing this box along. So what are the non-conservative forces here? The non-conservative forces are the push and friction. So the work due to non-conservative forces will have two sort of sub-works in them, essentially. So you've got the work due to non-conservative forces is equal to the force of the push times delta x, and that's positive because delta x points to the right, push points in the same direction, but it's going to be minus Fk delta x because friction points against the motion there. So this is the expression for the work due to non-conservative forces. And so we're going to say, again, with our main formula, we're going to say E initial plus the work due to non-conservative forces equals E final. Again, we're on a flat surface, so we only have K initial plus F push delta x minus Fk delta x. This whole thing is just work due to non-conservative forces equals, and then K final in this example. Okay. And we could fill in more information. Maybe if we're given the mass and we're given some more numbers, we could find something. But this isn't really framed as a concrete problem. It's just this. I want to bring your attention to this. This term, this combination of two terms right here, is the work due to non-conservative forces. Okay. So the last piece of this puzzle is that I just want to emphasize gravity doesn't show up here. Okay? You do not put gravity in as one of the non-conservative forces because it's conservative. Gravity has an associated type of potential energy. So if this whole problem were instead on a ramp, you would still have F push delta x would be along the ramp. You'd still have this friction. You would have UGs, gravitational potential energy showing up, maybe at the beginning, maybe at the end, it depends on the problem, but you would not need to modify this. You would not put any work due to gravity in this term because gravity is a conservative force. And later, when we start talking about energy with charges, charges will also be conservative. So it's really like extra outside applied forces, friction, air resistance or drag, whichever you want to call it. Those are the forces that can change the energy of a system and go in this term due to the work due to non-conservative forces. So this basically is a way of combining the ideas of work into our larger idea of conservation of energy. Energy initial equals energy final, even when we have situations where energy initial doesn't equal energy final, we put this sort of, you can almost think of it as a correction term or an adjustment term. The energy initial plus this adjustment This number might be negative or positive, but plus this adjustment will give you the final energy. So hopefully that's clarified that, and you should now be able to solve problems where you have non-conservative forces changing the energy of a system.